Hey everybody, how you doing? It's Pierre Hulsebos from Microsoft. Today we're going to talk about some Dynamics Field Service and really resource scheduling and our optimization engine for resource scheduling. We have some sponsors for this, and I hope you have an opportunity to check out their web pages and sites. These, without sponsors, this doesn't happen. We need sponsors to help pay the bandwidth bills and keep the coffee pot going. And so we thank all of these great partners for their continued support in our solution area and helping bring education to our community. My name is Pierre Hulsebos, and I am a global black belt on the Microsoft team. What that means is, I just eat and breathe and think about field service workload every day. For me, driving the dignity in the workplace is such an important component. I come from an area, and you're going to find out all about me today on this presentation because, quite frankly, we are working with folks that are right on the front lines, folks that punch a clock, that get in trucks and go out and fix things and make stuff work. And we just love that group of folks, and we want to help them and empower them to do more. And that is our goal here at Microsoft, is to empower every person on the planet to do more. And so this cadre of folks, this customer base is what we're talking about here. So really excited about our discussion today, and hopefully you'll see some of the awesome value that we have. So you can get a hold of me on LinkedIn. You can also look me up on Facebook or up on our friends at the Twitters at Infuse Me on Twitter. Okay, so that's some background for Pierre. Now, one other thing is I'm in Michigan, which is because I know we have kind of a global audience today. So we're in the heart of the Midwest, and Michigan is known for cars and music. So we're going to talk about actually both of those things today, which would be kind of cool. So when I saw what Mark and team had put together for this event, and we looked at some of the slides that they've got and some of the stuff you looked at today, I just thought, Miami Vice, man, this is the color scheme for Miami Vice: pink and chartreuse and kind of the squiggly lines. It's kind of a very much America mid-90s or late 80s and mid-90s. Now, if you don't know what Miami Vice is, this is important. This is our lesson for today. You're going to walk away with learn some stuff more than just resource scheduling. You're going to have some good context to why this is important. Miami Vice is an American television show, a crime drama that was made in 84 to 1990. So it was on the air for about 5 or 6 years. They made about 100 episodes of it, and it was really cool show because it used a lot of pop culture in it around it was groundbreaking. It had a beautiful color scheme to it, and very influential show. But there's two parts of this thing that we want to really talk about, because when we talk about optimizing schedules and resource engines, what we're really also talking about is resources and vehicles. So I want to hone in on vehicles, and Miami Vice had some of the coolest cars there was. First was the Crockett. He drove around the Ferrari Testarossa. That is a V12 engine, 4.9 liters. It could do 0 to 60 in 4.7 seconds. It was a burner. This is a hand-built car made obviously in the Ferrari factory there in Italy. And now the one thing back then, because gas was like real cheap, that was like $1 a gallon. His a really bad gas mileage. That thing got 9 miles per gallon, and this is going to be important, so pay attention. 9 miles to the gallon. If we were in person, I'd be having a quiz here and having people guess how bad the gas mileage was. So 9 miles to the gallon. Now, this was Sonny Crockett's car. Tubbs, he, of course, is an American icon. And so he, of course, had to drive the iconic American car, which is the 1964 Cadillac DeVille. convertible. This was the first year that the convertible was in the DeVille. They made about 100,000 of these cars. It was car had air conditioning, hydromatic shifting. This thing weighed 4 tons. This car was giant. It only cost $5,000 as opposed to the Testarossa, which cost about $1 million. But this was a 7-liter V8 engine, big car, very American. Put out, didn't do 0 to 60 in 4 seconds. It took about 8 seconds to get up to 60 miles an hour because it had a 300 horsepower engine. Now, one of the most important things that you could learn today, walking away from this, now you can share with your kids a little about cars in Michigan. Now, this car, this beautiful car, this Cadillac was designed by this man. His name is Bill Mitchell. Of course, he's from Michigan in Detroit. He designed the very first Cadillacs. And so when you look at a really cool car that has tail fins in the back, which is a big one of the design parts of Cadillac, even today they still have that fin design on them as part of the design language they use. That was his invention. He also designed the first not only Cadillacs, but he also designed one of the most iconic American muscle cars ever that was given to every astronaut that went and flew to the moon. It was the Corvette. Man designed the Corvette too. So the Cadillac and the Corvette, two of the most beautiful cars made in Detroit. So if you here in Michigan, we like to help you fly to the moon and back and drive fast cars. Maybe sing a tune or so, given Motown. But this is where we're from in the Midwest. Now, anyways, I'm getting a little off track here. I want to get back to vehicles. Holmes over here and Tubbs and our buddy Crockett drove around this 38-foot Scarab Boat. This thing would go to, it was a giant twin V8 engines in it with 7-liter engine, Merc cruisers that cranked out over 500 horsepower each. So at full bore, this thing is putting out 1,000 horsepower and got 53 gallons an hour, which is pretty close to basically 1 mile a gallon. So this thing was a total gas hog, if you will, but man, it looked cool and could go fast. And man, if you were out there trying to shoot the bad guys and keep drugs off the streets and all the ladies happy, this is the thing you wanted to drive. And anyways, another Michigan fun fact here. Actually, truth be told, in the first season, when he was in the first season of Miami Vice, he drove a boat that actually was built about 20 miles from my house here in Holland, Michigan, by a company called Chris Craft. And Chris Craft did boats in the first season. When you think Chris Craft, think mahogany, handmade, handcrafted boats from the 30s. This was really their boat. This company actually went out of business and right in the middle of the first season, so they didn't get the contract for the second season. Now, why is this all important? Anyways, why is this all important? Well, here you go. Here's why this is important, because we want to focus on how much it costs to drive these vehicles around, from the boats and to do all of this stuff. I worked out all the math on this one, so trust me on this. Over 111 episodes, if they drove, both of them would have to drive their car, right? In that, so what they would do, and they had to drive their boat. So if they drove their boat for the 100 hours and they drove their cars for the 111 hours, this is what they would end up with consuming in those really bad gas mileage vehicles. About 8,000 gallons of gasoline, which also equates to about 130 metric tons of carbon emission. So these guys, let's just say they weren't happy when they got the bill. The captain probably didn't like signing that bill. It's very expensive to drive those really bad vehicles around in terms of their gas mileage. So this is just one of the ways to think about where resource scheduling optimization can help, because mileage and time is worth money to our customers. And there's an impact to when we're driving around too much, right? So let's just talk a little bit about what a formula that you can construct in terms of ROI looks like, because before we get into how the tool works, we really want to set the stage for what this tool gives us. Why would we be interested in this? What is the benefit? Well, here's the benefit of this system. So we're going to start kind of with that. We're going to talk about features later. We'll talk about benefits and ROI first. The benefit really here is in two things. One is the first part, which is pretty simple. Everybody can get this part, which is the vehicle cost itself down here. What is the cost of the vehicle? You know, we can see that, let's get a little highlighter here or something like that so we can help. Let's do a little laser pointer. No, come on. All right, so why my laser pointer part isn't working or highlighter isn't working. All right, we'll try highlighter. So the first part is the vehicle cost. The vehicle cost here is the first part that's the most evident, obviously. So we want to kind of give you some numbers here, and we're just going to throw some numbers around. These are not by industry averages. These are just some good numbers that we can kind of help construct this conversation. Your mileage will vary, basically, as they say. So let's focus first on the vehicle cost. So that's the cost of maintenance and the cost of the payment for the car, the insurance, the actual car itself or vehicle itself. So this is going to vary widely, but this is a pretty good place to start. Most, if I'm putting let's say a heating and cooling technician in a panel truck, and it's got the ladder on the top, just a normal, truck, a little pickup truck, or I'm driving in a pickup truck. This is kind of the mileage that we would see with a vehicle like that. Anywhere from $150 to $250 a mile, right? That's just the miles cost. So we're going to use $2 for that calculation. So every mile that we drive, and if we drive 60 miles an hour in this, we're just going to again use some round numbers. That works out to $2 a minute, or a dollar, so $2 per minute per mile. The other one is the technician time. The technician sits there, and so I have to pay him. I have to pay that person or her. I have to pay that person for that work, right? So just the regular labor sitting there, you need to know what the burdened labor cost per hour is for that person. Now, so I'm putting $30 an hour there. That's not a lot, relatively speaking. Technicians and engineers that do this, any kind of work that is of the level of significance is going to make their burden labor cost is much higher than this. But again, we're just going to use this to just as a placeholder number. The other, you have to double dip that number. You have to double dip that number, because why is that, Pierre? Why is that? Well, if this person is a resource and his time is or her time is money, when they're sitting doing nothing in their truck driving, I have to make up for that billable rate. So I have an opportunity cost that I'm losing by not having that person fixing something. So that cost also has to come into play. And again, in our calculation, I'm going to put $30 in there. That's really way less expensive than you would think. This cost for some of our customers could be $75 to $200, depending on what their billable rate is and utilization is. So you basically have to take their average utilization for the year. Let's say for a technician, it's 80%. And that dollar amount has to be equated in what they're not billing when they're driving. So in our little fake world that we built up, this adds up to $60 worth of labor costs per hour. It actually, just again, when I ran a service department, I would have this argument with my customers every once in a while. They would say, hey, I am not going to pay for you to travel to my location. And I would say, Mr. Customer, you're going to pay because it's actually more expensive for me to have the guy sitting in the truck driving to you than it is for him actually to be there working. So let's split the cost. So a lot of companies figure out a way to pay that. Some of them don't. Some of them we just do a trip charge. Other places we don't do that. So in the case of a lot of asset servicing, when we're servicing our own assets, we don't even have a way to recover that expense at all. So with that is we're going to stick with $1. So basically what that means is for every hour, so we take these numbers right here, $3 per minute or per mile, because we're driving 60 miles an hour, which is 1 minute. So every hour that that person is in their vehicle driving costs my company $180. So let's just put that in perspective as we look at looking at the big numbers and how many miles different companies drive. We've got customers out in like West Texas that are working in the oil fields, going out and doing inspections on those oil fields every day. And so they're going around to wells and doing that, and they can drive up to 100+ miles a day. So if I can impact 100 miles a day in a calculation like this, what would those numbers be, right? So 100 miles a day, that's $1,800. Just think about that, right? That's amazing. $1,800 a day. And so if I can impact that by, let's say, 10 or 15%, that is at the end of the week, I'm saving a company up to $500 per week per technician. So if you have, let's say, 100 technicians, that is a boatload of cash, right? So there is real money on the table for this. So I think that's why this is such an important thing to consider. So resource optimization gives us, this ability to improve the efficiency of a person, not make them work harder, not berate them because they're not doing something right. It's actually just using math to come up with an optimal schedule for that person. And not just the individual, but a whole team of people that go out and do this work. We're reducing the time that they sit behind the wheel driving. That is the biggest ROI. So if you have a customer that has, or you're a customer that is handling, your technicians are handling 5 work orders a day, and I have 10 of those people, we get into the thousands and thousands of permutations in terms of optimizing that schedule. And it gets very difficult, if not impossible, for a person, a dispatcher, in their human capacity to manage the complexities of that schedule better than a computer can do math, because it's just a big math problem. So we improve the efficiency, we give them back their time, and then there's another effect that happens, which is customer happiness. Customers love it when I send the right technician at the right time to do the right job. And so that seems like a pretty banal kind of mediocre statement, and that's been a kind of a brand promise to CRM, the right person, the right time, the right place, all that kind of stuff. Got it. But what happens is when a customer contracts for service and says every month you're going to come out and do this inspection, when you actually perform that inspection within the time period allotted and you do it efficiently, you maintain the equipment better. We show up when the customer is expecting us, and so everybody's happy in this transaction, and the equipment is maintained properly. So we always see higher levels of customer satisfaction when we are making a promise to the customer and we deliver on the promise. And so let's just think about it in the broad sense of how the service application layer works with the CRM system. The CRM system captures the customer's expectations, right? The CRM system goes and says, this is how much you're going to pay. This is what we're going to do. The service side of the application picks up the customer story from there and brings the journey through to the promise that we made in the sales process to service the equipment or the products that, or do whatever installations we're going to do. So this is the system then then that fulfills that promise. And when we can tie those loops together, this is the promise, this is the fulfillment of that promise, customers get really excited about that stuff. They're more likely to buy again from you. They're more likely to engage with your team again. And it just makes everything really awesome. So with that said, let's move on into talking about, like I said, we talked about benefits first. Now I want to spend the rest of the time today talking about some features within the application. So the first thing that we need to do before we get into the actual demo, let's just talk about field service for a minute and kind of at a high level what the field service application does. You may not be familiar with the field service solution, so let's talk about that for a second. So with that said, here we go. The field service sits inside, as we mentioned, this kind of ecosystem of solutions and applications that are part of the field service system. We manage demand. Work orders are at the heart of that. You're going to see a work order here in a minute. You'll see that that's at the heart of it. Those are where the demands come for the service department. We generate work orders, whether they come from projects or agreements, or the customer calls and said something's broken, please come and fix this. We have the ability to pull alerts in and look at things there also. So we're pulling in the work, we're planning the work then. Who's the right resource, when's the right time, and this is where our focus is on today, is planning the work. And then from there, we give work out to the technicians and we engage customers and we can analyze the whole thing. So the field service application is part of an entire ecosystem of elements or entities that are part of the Dataverse, like service level agreements and invoices and products and inventory items and transfers and purchase orders. All these different components are all part of the application itself. Not only do we have this tremendous pipeline in terms of business process applications, it sits on top of rich layers of this common data service, works with all the other Dynamics 365 business applications. We integrate very seamlessly with mixed reality in terms of asset capture and guides. We have a lot of different features in terms of pulling things in. And we're talking today about a feature around machine learning is what we're talking about. And that's where we are taking machine learning engines and pointing them at the schedule and the demand planning that needs to be done. So what we're really trying to do is scale right now. This is the main problem that folks are trying to address. We want to be able to scale the technicians' productivity by doing a better and more intelligent scheduling. There's many different ways in Dynamics that we can attack this problem around inefficient allocation of technicians by doing different things, enabling remote assistance to improve the first-time fix rate, to reduce break fix by doing a better job at maintaining things up front, or in this case, we're going to be addressing the inefficiency of scheduling and the problems that are inherent in the scheduling system. Now, as you look at the application, as we said, we have work orders, purchase agreements, and things on this order that help manage the demand, plan the work through the scheduling board, enabling technicians through the mobile application layer, and engaging with customers in a whole bunch of really awesome features like portals and technician tracking, notifying customers of when things are not working, and also being able to use AI to help analyze the streams of data that come out in order to help take care of customer needs. So with that said, let's just bring this over here to look at the application. So we're just going to log right in here. We're in a Dynamics field service solution here. I'm going to change my resolution here because I'm on a little smaller monitor than I normally would be. All right, does that look okay? I think that looks okay. Okay, so what we have here is, as we mentioned, the heart of the system that we have is the resource scheduling optimization work optimizes our work orders. So inside the system, you would have a work order that comes here, and this is a work order. Work order contains like the tasks that need to be completed, the products that are on there, anything that we need to do as we work through this. an important, there's there's three important elements here in this. One is we know the priority of the work order. So work order priorities are going to be important because we have different priorities in the system, and I've just matched them up. We have kind of high, medium, low kind of a thing on a scale of 1 to 10. And so you can set up all sorts of rules to prioritize one work order over the other. This is what a dispatcher does normally. They're able to look at a work order and go, well, that's not as important as the other work order. These are the ones that the customers just called in because something was broken. These are planned maintenance work that doesn't have to be done for another month. A dispatcher wouldn't treat those two differently. The system doesn't treat those two differently, or treats those two differently because they are different priorities. So we have priorities within the system. We know the type of work that needs to be done. It tells us I need to have a technician to go out there and set up a service task of doing an inspection. So this is an inspection work order. So it's basically saying I need an inspector to come out to this location. So the system also knows the geolocation of where the work needs to happen. So in this demo data set, or this data set here, we're working in Melbourne, Australia. We're working on the water project, or we're working on their utility system there in Melbourne, Australia. So these are work orders related to that. It has, of course, a business process. We're just right now in the process of, we've established scheduling the work order through this process. So once something is scheduled, it continues to move through that. So the work orders are kind of at the heart of this. This is what is going to get scheduled. This is what's going to show up on the mobile device to say, Pierre, you need to go work on this particular work order. So the other part that's important here is we have what's referred to as the Spencer Lowe. He is one of my bookable resources. He is a technician. He also has similar qualities to him. The records in his system tell us what we refer to as the characteristic or skill that this person has. So let's say I need a pipe fitter, or this particular type of job that has a union skill, or they need to have their safety certification for this year. What are all those, we call those characteristics? These are associated with the actual resources, the people that go out to do the work within the system. Of course, it handles, what's their expense layer, and more importantly, what their work hours are. So we can see from this schedule, we see that Spencer works every day. And so he's got a capacity of 1. And this is what his working hours are for this day. He works from 2 p.m. to 12 a.m. That's his shift. So he has like a second shift job within the system. We want to know, the system knows where he starts his day and where he ends his day. So we're going to pick his address. Some folks, we want to start at their home. Some technicians begin their day, they drive into the office and they pick up a truck or a vehicle. And so they start their office from where their office is, or organizational unit. Other technicians go into the office and work comes to them. It's bench work. And so their scheduling is really agnostic of the location that they find themselves at. And then, of course, we've turned on the resource optimization. Oh, let me add one more point here on the scheduling component, because this is something we added and it's just the coolest thing. So we, of course, show them on the schedule board, but we had added this feature here to allow for travel before work hours. I can also allow for travel after work hours if I want to. So, and how many minutes do I want to allocate to allow this person to travel before their work day? And what this bottom line means is, if I have a work order that is booked for today and my business hours are 8 o'clock, I want to start that job at 8 o'clock. I want the technician walking in the door at 8 o'clock. Well, if we didn't allow for the system to calculate the travel before 8 o'clock, we would just have him leaving at 8 o'clock from his house. So we don't do that here. We allow you to say, I want to start my job at the house I want to allow the system to schedule that person to leave at 7 o'clock in the morning, so they show up at my business hours or at the customer's request what that time is. So we allow the system to calculate travel outside of his working hours, which is really cool. Really, really cool. So that's kind of what the resources are. If there's any questions, please let us know. We'll talk about some of these at the end of the thing. So now with that said, what we want to talk about is the actual scheduling jobs themselves. Let's see, pull up here. Sorry, here, let me pull up because I think I clicked in here. Sorry about that. So, okay, so we have what we refer to as the optimization schedules. Pay no attention to the failed because it's turned this engine off, so it's trying to run it, but there's no underlying engine's turned off at this point, so it looks like it's failed. But anyways, we have different jobs that are scheduled to run within this system, and so I'm going to look at my base schedule for that water quality team out in Melbourne. The water quality team has an optimization schedule that's set to run every day. So it runs on a fixed timer every 8 hours. So every shift, it goes and does this scheduling job again every time. There's two main and let's talk a little bit about this for a second here. So I can filter to say, I don't want you to run on certain times of the day, or don't run on the weekends. You have a lot of kind of finite control over the little fiddly bits here around when you want this to run or don't want it to run, etc. So, so this job will run. So that means what I'm saying here is I could have other jobs that run in a competing schedule, have different sets of scope, different rules that I might have for them. So this is laying out a baseline schedule for the whole organization. And then I might have another one that runs every 4 hours that resorts the current day's scheduled work based on traffic or something like that. So, so I might have a traffic optimization that runs throughout the day, as if I'm here in Melbourne, so busy traffic, there might be an accident. Traffic is going to affect my ability to show up on work orders, plus people might cancel, work might go over what we had initially planned, and so now I've double booked people or I'm not showing up. So I want maybe the system to look at that and re-optimize the schedule every 4 hours throughout the shift. So anyways, that's another kind of design model, and this is why this engine is a little iterative. When you get into production, you kind of run through some of these different scenarios. So anyways, let's keep drilling into our water quality here team. So they have a 2-week schedule. So this is, there's two elements to these in terms of being able to tweak and have them do certain things. The first part of it is called the scope. The scope itself is what it does. The scope allows us to basically tell the computer, tell the job what work orders we want to choose for it to consider. So behind this is a view. You build a view inside of the system of, here's all the people or all the resources that I want you to optimize, and here's all of the requirements and work orders that I want you to optimize. So this allows you to take the universe of tens of thousands of work orders and say, this is the job specifically for Melbourne, for this team, for this set of time. And that's what it's going to do. So this is basically looks out to 14 days. So I'm looking out to work orders that have a promised time and a must do time, basically within every 14 days. So every shift, that window of 14 days is moving along. So tomorrow it'll look 2 weeks out to tomorrow, and new work orders will come into the scope, and other work orders will fall off the scope. So this is going to optimize for 14 days. I have a set of requirements too that are part of that. And what are the resources? So I have a team that I built a little view in that says this is the particular set of all my 800 technicians. This is the 20 that optimize this region. And you have other things like we call them offsets, which allow us to kind of slide that window back and forth. When I run the optimization window or optimization jobs, I want to usually offset the time to not do it now because we might be in the middle of a work order. I want to maybe offset that for an hour or 2 hours or something like that. Depends on the average size. Typically, it's the average size of your work orders. So if we're a mid work order, I'm not going to reorganize everybody's work order that's already in there. And how far out do I want this to go? I'm saying for 15 days. So I'm looking at 2 weeks worth of work and I'm scheduling it for 2 weeks worth of work. So take 2 weeks worth of promised work orders and schedule that against a 2-week time window for my resources. You can filter out by booking status. So booking status is, if work orders are canceled, do you want the system to redo those? Or if the customer, do you have other ways of dealing with canceled work orders or policies? Things that are committed or locked in or not locked in. A lot of folks have kind of nuances around when they make commitments to customers. Other ones are like soft booking the resource just so I can hold it. And then later on, I might reuse that time slot or recover that time by by overbooking or, all these different things that you can do. And so that's what this is setting up for here is what we call the scope. Kind of what are all the work? The next part, which is really the kind of the heart of this, is when this job runs, it's going to have a goal to run. And what are the goals of this particular job? Well, I've given it a name. This engine effort level is, we can kind of come back to this. This is one of those things where inside of the scheduling engine, at a certain point, the system will reach kind of a point of diminishing returns as it recalculates and recalculates and recalculates and thinks, well, let me try it again with this little optimization. Let's keep doing it again and keep doing it again. At some point, it reaches kind of doesn't get any better, and that's when the engine stops. When you start running this within the scope of the work orders of these, that time that the engine takes could be anywhere from 2 minutes to 10 hours or however complicated you want the job to be. So this allows you to kind of tweak that setting in terms of the time that you allot for the energy or the effort of the engine. If very intense, it's going to take longer. If I make it very light, it's probably just going to take the first pass at the math and just go with that schedule. Even though it could, if it worked a little harder, could find a better, saved you a little more money on the travel. This is something that we've done with or without historic traffic. So obviously we work with Bing Maps, is a property we own, and it does a great job of knowing historical traffic times, and it knows how much time it takes to drive that same exact route, whether it's 10 o'clock in the morning, 8 o'clock in the morning, or 5 o'clock in the afternoon. That same route, if you've ever driven from the Microsoft campus to the airport, which is only about a 25-mile drive, that can take 2 hours or it can take 25 minutes. Just depends on the time of day. So this engine takes that into account, historical travel as provided by real-time traffic and all that kind of stuff. So it's pretty cool. So we use historical travel to help there. Now gets into the tweaky bits right here. So what we want to do is we want to set up some objectives first. Let's talk about objectives. So this job has a very specific set of objectives in it. It's going to, first I want to meet high priority requirements. So I really want to emphasize for this particular job, if there is a priority 10 job, it's going to beat, so to speak, a level 2 job. And so this is where the system does that math in terms of looking at all the work orders. If I had more work orders than capacity, basically was what we hope happens. I have more work orders in the system than the capacity to perform the work. And so then I want to take and say, well, I'm going to discard all the low priority ones first. So that frees me up. So now I know I have the amount of time that I can fit all this work in. So this is kind of what it's doing. The other reason is I want to match the best skill level. So when I'm picking, I want an installer, and I have 2 resources. An installer has a rating of 1 and another person has a rating of 2. It's going to prefer the higher skill. It's the best matching skill level. So it's not just the skill, but it's looking at the levels of folks in their competency layer. So we're matching that, meeting the required competencies here in the constraints. So we're only going to book work orders where somebody meets the specific requirements. So if it's a technician that is a installer, let's say, and I don't have any installers anymore in my pool because they're all booked, we're going to miss work in this particular one because we're making sure that we always meet the characteristics. You can turn that off, and again, this depends on the policies and the rules that you're trying to set up. We want to schedule it. We want to minimize the total travel time. So the thing to consider is when you put it, the travel time, wherever you put that in the hierarchy here, it's now going to look at all the things that we just picked. We pitched the matching skills and we pitched the highest priority ones. So we tossed out all the low priority ones, and now we're going to take that and optimize that for travel. So once you lock into travel, all the ones below that, it's hard to actually have them to have any effect. In actuality, there's been a lot of studies done on this, on resource scheduling engines. And once you get more than 3 sets of characteristics, there's a very little impact that 4th, 5th, and 6th one has. Because again, once you've optimized for travel, you've locked it in. How can I unless I can make an assignment that keeps the same travel budget, but minimizes or maximizes the work hours. If I can fit some more in there, I will. But once you hit that travel, so the thing to know about this is that travel can't be the first thing you do. It cannot be the number 1 priority. You always have to have one. The system will not let you make that the number 1 priority, because once you lock in for travel, everything beyond it, it's, unless resorting that engine again comes up with a more optimal travel schedule, it doesn't make any difference. So anyways, that's how the jobs are set up. And so we have our job that's set to run on a schedule. It's running at a certain set of time. You can set date ranges for this of when you want it to run and when you want it to end. So you can set up future versions of the schedule. You can then have a weekend schedule and a weekday schedule. So you can have all sorts of different schedules that run. So that is one of our visions within the system. Companies that are doing this really well have multiple resource jobs running, scheduling jobs running to help scale. The system runs work in parallel, so we can scale this up. It uses an elastic Azure back end on the AI engine, so it's very performant. It go very fast when you consider the math. I'm not going into the math here, but when you think about the amount of permutations the engine has to go into, it's an astronomical sum. It is a geometric progression in terms of the math curve, in terms of potential calculations. The more resources that I have, the more work orders I have in my scope, and the more frequent I run it with each one of these different characteristics. A small workforce doing a couple weeks worth of work in a scope like this, it had several hundred work orders to deal with over that 14-day period. The engine ran fine once it started running. After the first couple times, it gets actually faster. The second couple times that it runs, there's some caching apparently that goes on within the system. This particular one would take about 5 minutes to run. So not a lot, but when you look at the number of calculations, it's actually in the billions of calculations that it's doing in terms of math and resorting and whatnot. If you're really interested, I'm not a math whiz or anything by any means. I'm not very good at math, but anyways, it's a giant number. It's a giant number. Anyway, so what happens is this thing runs on a schedule. And so what we see is the effect of this schedule. And so I just want to drive in here what the schedule looks like when it's done. So let's take a quick look here. The schedule looks like this, is that we have our technicians here. So the system's laid in all the different work orders. Now, the first thing that you'll notice here is that the work orders, there's no travel time between all these different work orders. And so what the system has gone and found is all of the work orders that are at the same job site. And so again, this is what we're trying to do, especially with a lot of maintenance work. This is a utility system. So it's a lot of like going and checking the valve and going and doing this inspection and inspecting a lot of equipment. And so this is what we're planning to do here. So it's going out and finding all of the common work orders are at the same locations. And the other part here is, so like technician 2, as you can see, what it's done is it's found where this person is going to do their day and start out. So it's a 50-minute drive. They're going to do these sets of work orders, and then they're going to drive around the corner. As you can see, the little animation, it kind of shows you starting the day here. And then I'm going to go to this location, and I got 2 work orders, and then I'm going to drive another 20 minutes, and I'm going to go back to this location, and then I'm going to drive right around the corner to this location here because I'm coming back home. And then you can see I kip off at the end of the day at 4:30 in the afternoon. And so it calculates that travel time back home at the end of the day. And so you'll see a lot of these have nothing after the last one, this little blank spot, which is still working hours for this person. And so it's letting them travel back home to get home within that working hours window that we set for this particular resource. And so this is the kind of thing that you love to see the resource scheduling optimization engine do, is that it goes out and finds all of the like work orders for a person. It lays them in a logical and mathematically competent optimized driving day for this person. It's taking into account the commute, both to the job and from the job home at the end of the day. And we're seeing this here because what my impression here is what this has done is you know, we're seeing here again, the drive out, the drive out. They're starting, here's their home location here. So it's the drive out to the place. And then as we get back here, so it's it's starting with the furthest location away. And then we're now going a little further to the east, a little further to the east. And then we're going a little back to the west, and then we're going back to the west again. And now we're driving home. So it's kept all of these in a close proximity to each other, and that now allowing this person that drive home at the end of their day. So meeting all the requirements of the person, all the requirements of the customer, and all the requirements of the jobs that have been put in front of it. And that, in the heart of it, is what the field service application is doing with the resource scheduling optimization system. Now, I'm not going to go into all of the details around the reporting aspect that comes along with this. We have some good information on our website. There are metric jobs within each one of the systems that you can that show the compiled set of here's all the jobs that have run, how long each one of them takes, how many travel miles we have calculated for each one of these. And so as a user, you begin to establish baselines for a job like this. Is it running fast enough? Is it the right scope? And what is my average travel time for this sets of jobs? We can also look at the utilization of each individual. And again, these goes back to our Crockett and Tubbs. What is their utilization? What's their real expense? And so this is allowing me to look at things like what is their utilization? How often are they performing on the schedule in terms of arriving late? We promised a time that we were going to send the customer or the technician out. Are they arriving back in time? And how many miles they're traveling, how many miles per day. And you can set all sorts of, look down at a specific individual resource or looking at a whole set of folks and kind of help really analyze the individuals and their performance against those metrics. So you're able to tweak the job itself. Like, as I mentioned, this is kind of iterative process. So you're setting up the job, you're running it, you're letting your technicians run out there and go do the work, and you're coming back. How efficient is that particular job, and is it performing well? one of the things that we have found anecdotally in the field is that some dispatchers aren't so keen on this system because they believe they can do a great job. And again, the math and scale is so giant with doing efficiencies in here. Every time that we have run this engine against a person's ability to do the time, not only does it take less time to do it, they usually come out with a more accurate time estimate using this system. Now, that's no knock against dispatching at all. For some customers of ours, it's not that way at all. The dispatchers are just fine at doing it because the jobs they have aren't as complicated, or there's not as many work orders. The efficiency comes when we add more work orders per day, typically. So a system like this, where we have a lot of inspectors driving around doing 1 and 2 hour inspections, especially in a metro area, got 30, 40 technicians looking at 2 weeks worth of, these are hundreds and hundreds of work orders. So a system like that is always going to beat a person. But if we have very linear kind of runs, and anyway, so those are some of the points. I want to thank you all for your time today. I hope you have just an awesome rest of the event. And thank you so much for your kind attention to Microsoft Dynamics and our field service solutions. I hope you have a great day, and I appreciate y'all and what the Scottish Summit's going to do. We wish we could do this in person. Hopefully next year we'll be able to do this in person. And you guys and gals have a great day, and thank you so much for your time.